have this question in your notes? No? No. Okay. I aspire one day to have a semester where I get everything right all the time. So let's just think about this, new flu shots. So every year we have to get a new flu shot. We've also been experiencing this with COVID shots, that the COVID shots haven't quite caught up to the immune system level of changing as quickly with the variants of the COVID shots. But so this is a really interesting thing, and especially for any of you who are interested in like molecular biology. There's a whole field of really important research, and we're going to see that again with COVID as well. This is another one of those vaccines that every year will be changing with what has been happening. Is there are people around the world that look at the data of the genome of the flu virus from last year and the couple previous years, and they think about how might it mutate. So have any of you ever gotten the flu shot and then the flu starts going around and you still get the flu? Because the flu shot is not always spot on. Sometimes, so the whole field of research about flu shots is that they're predicting what's going to happen the next year, and sometimes they can't. I mean, because we know that mutation happens unpredictably and all by chance, it's not a perfect science in predicting what's going to happen the next year. So sometimes they get it wrong. So one of the things though, if you remember, that the avian flu has human flu components to it. So even if, let's say this year that they had the flu vaccine not spot on, if the avian flu, which we've heard a lot about that, and avian flu, we'll talk about one of these zoonotic diseases where it starts with another animal and crosses the species barrier, which is not super common, that because there are human components that going from avian flu to infecting humans, or sorry, I should say, going from infecting birds to infecting humans, that because if you get the flu shot, you have a little bit of protection there. So I have a friend who said, I never get the flu. I said, well, that's lucky. That's just luck that, for whatever reason. And she's like, well, I have an immune system against it. I have immunity against it. I'm like, no, that's not the way it works. You've just been lucky. And then I told her about the protection of the avian flu, and she went, oh, maybe I should get the flu shot. I said, that's something to consider. So I like to give people data and say, here you go, think about it. Avian flu, I started talking about that and I went in a different direction. Avian flu is typically, the way humans have contracted it is that you have direct contact with a bird. It's not respiratory, like what we're seeing with the flu and COVID. So it doesn't travel in the air. It's not a respiratory contracted in terms of like floats in the air. So if it ever mutated in a way that it could become respiratory, that's where it could become an issue, but we're not there. It hasn't happened. Bless you. So every year, flu shots, why every year, around the late summer, going into the fall, they say, okay, it's time to get your flu shot. It changes, the flu virus mutates, that when people contract it inside of their cells, and your cells are programmed to replicate the virus very quickly, that in that quick replication within our own cells to make more flu, that mutations happen. And we'll get into that in a little bit as to why. Okay, so our immune system, we have this amazing defense system against anything that might come into our body. We have different lines of defense depending on what we're talking about. So in terms of what could come into your body, so just like a sneeze could have been caused by a piece of dust floating in the air. And your body responds by trying to get it out. Because your body, when you're breathing in and out, as you're sitting here, you're not thinking about it, and maybe there's some just dust particles from us walking in the room and dust was stirred up as we walked in, that perhaps inside of your nose, you have these little tiny cilia or hairs, that piece of dust could settle on one of the hairs in your nose, and your hairs in your nose vibrate in a response to something. It could be a flu particle, it could be COVID particle, it could be dust. And it responds by vibrating, and that vibrating causes like a tickle, right? You ever feel that? You get like a ooh, and then you cough or you sneeze. And it's just trying to get it out of your head area before it gets inside of your body. So we have just very simple lines of defense to very sophisticated, very specific lines of defense. And this is one of the things about the immune system that's so amazing, is that we're just trying at first, your immune system's trying to just keep everything out, to keeping specifically flu, or attacking flu, or attacking COVID. Okay, so the first line of defense is called non-specific. It's not specific outside external barriers, meaning just like a wall. Anything from the outside is going to be try to be kicked out. So we get those things like, right, like sometimes you have like a tickle in your ear, a tickle in your nose, your eye, you feel something, right? If you get something in your eye, your response is to do this, right? Start, oh, my eyes start. Your eye is blinking because it's trying to push out anything that's coming in. So those kind of like tickle responses are part of this non-specific external barrier. Okay, so let's talk about some of the specifics of the non-specific. So one is your skin and your mucous membranes. So let's talk about skin. Your skin has, if you've ever kind of taken a look at skin, it has a lot of layers to it. And it's got these living layers, and then on top it's got non-living dead layers out the outside. And those kind of drier outside layers, which become more apparent over the winter time, right? If we're in a very dry environment, the humidity goes way down in the winter time. And one of the things that we notice is that our skin gets dry. You see that drier. If you have flaky, right, it might be flaky. So that you get this kind of like flakes that you know that top layer is dry and dead and becomes more dry with less humidity over the winter time. One of the things about the strategy of us having that kind of dry, dead layer is that it's really hard for anything to live on. Remember when we plated bacteria, the E. coli at the beginning of the semester? You used a jelly, like a Jell-O, nice and moist, and it had nutrients in it. And we put it in a warm incubator, which you didn't know that step, but it was implied. And we put it in this nice, warm, moist environment. And that's good for growing things on. Whereas if we just put it right on, if we just plated it onto, if we took the E. coli and we dipped it into the solution and the nutrient broth, excuse me, and then we plated it onto the plastic with no agar in there, none of that Jell-O, it would dry up. And then we put it into the incubator, it would just dry up, because that's a really dry environment. It's kind of like our skin. A very dry outer coating, so that microbes, if they land on there, they don't survive very well. So that's one strategy. The mucous membrane. So remember I talked about the portals to the outside world. Anywhere you have a portal or an opening to the outside world, eyes, nose, mouth, ears, your belly button, nipples, underarms. So all of those places, and then the whole urogenital system where you have openings, that you have mucous membranes. It's a little bit more gooey in those areas. Just think about like earwax. right? Earwax is kind of like a gooey thing. One of the points is a lubricant for your hearing, but the other thing is that it's going to capture anything that's coming into that portal and protect your head. So mucus, think of like in your nose, right? If you're sick, you produce more mucus because it's trying to flush out whatever has been making you sick. So mucus, think about like gooey, moist, sticky, capturing stuff. One of the things that's contained within all of that goo are antibacterial, anti-anything really, enzymes called lysozymes. Lysozymes are contained inside of vesicles that will, when merged with something that we don't want, it's going to digest that thing. So again, it could be like just think like, they call it antibacterial, but it's really anti-anything digestion. It's just gonna try and digest those things before they can, from the portal to the outside world where we're talking about these places, to just keep it out from getting inside. So this is cool. Picture, you can see, as I mentioned before, the cilia, that anywhere you have those portals, you have more hairs, little tiny fine hairs called cilia, and those cilia have coatings on them of mucus, and they can just like, stuff sticks to those. So here you can see that. If something, again, touches the cilia, they start to vibrate, and you get that tickle, right? If you get a tickle in your throat, you're just breathing, and all of a sudden, you get a tickle. It's a cilia, something's landed on that cilia, and your response is to expel. Your body has an involuntary response to get rid of that. Okay, let's say that it gets past this whole head portal, and it goes into, one of the things that we'll get into when we talk about digestion and respiratory is in your neck, you have two major tubes. And those major tubes lead to, the front tube is the trachea, the back tube is the esophagus. Esophagus goes down into your stomach, and the trachea goes down and branches to your lungs. So within those two tubes, let's say that something gets into the trachea is lined with all those cilia, and your body responds by coughing or sneezing. And then if it gets into the esophagus behind the trachea, then you have stomach acids and enzymes inside of your stomach that will digest away of that, whatever got in there.
Is it, when something like goes down the wrong pipe, they say, is that when like you take a drink and is it going down your trachea instead?
Yes.
Okay.
Yeah, precisely. So that's a really good question. So in the front of your throat, you have the trachea, and then the back of your throat, you have the esophagus. And at the top of the esophagus, right, the esophagus is for eating and the trachea is for breathing. We don't want to get food and drink into our lungs. That'll just clog up your lungs. So one of the involuntary responses that you have is that when you're eating and drinking, at the top of the esophagus, you have what's called the epiglottis. Remember, we didn't dissect pigs yet. So we'll see today when we get into dissecting the pigs, there'll be like a little flap that looks like this. And it goes like that, and it covers up the trachea so that food and drinks slide down into your esophagus. And the epiglottis protects the trachea from anything getting inside. But sometimes you just take a drink too fast, and your epiglottis is trying to close really fast, and just a little bit of something gets in there. And it causes your response is to cough. Because a lot of cilia at the top of the trachea are activated and start to wiggle, and your body is like, gives a forceful response to coughing. Yeah. We'll talk about if something gets something bigger, like let's say that you're eating chili and there's a bean in there, and your epiglottis is closing, and that bean goes down into your trachea, and what if it's like a kidney bean, one of the big ones, and it starts to block your trachea, and it gets lodged in a way that even though those cilia are vibrating and you're trying to cough and you can't, it gets stuck. It's lodged in there, that you have to have somebody forcefully push it out and do the Heimlich maneuver. We'll get to that when we talk about respiration too. Okay, so let's say it gets past all of that, gets past your first line of defense. You have a second line of defense. The second line of defense are the non-specific, still trying to keep out anything. Doesn't matter. Piece of dust to a COVID virus particle. But these are internal, so it's gotten inside your body. And we call that the non-specific internal defense, or the innate immune response. Leukocytes. Leukocytes, as we mentioned when we talked about the circulatory system and different kind of cells within your circulatory system, leukocytes are a generic kind of white blood cell. Their job is to capture, engulf, ingest, so they're going to take something inside of their body. They're going to take microbes, meaning anything microscopic, means microbe, dead and dying cells. You sprain your ankle, you're walking and you go off the curb and you go like that, and your parts of your ankle kind of like rip open and you get a bruise. But when something, or you bang your elbow, right? You get a bruise on there. What happens is some of the cells open up. And then your body's circulatory system is going to bring leukocytes to that area, and they're going to gobble up any of the cells that have opened up. Because the danger with that is that as your cells are going about their everyday job of doing a million different things, is they have waste products from their production lines, all of their different metabolic pathways, that those waste products, we don't want them opened up and sitting around inside of our body. So the leukocytes, anytime you have damage inside of your body, the leukocytes are going to come and they're going to gobble up anything that's damaged in that area. They don't do it like, pretty quick, right? Over the course of maybe a week, you go from having maybe the first day it's just red, and then the next day it usually gets darker in a couple days, and then it starts to turn different weird like colors of red, and then like purple and yellows and greens, and that's because they're gobbling and they're working on getting that cleaned up.
So like once they gobble it up and stuff, do they like dispose of it somewhere else?
They die.
Leukocytes die?
Yeah, the ones that are doing the gobbling, they're going to have all that stuff inside of them.
Mm-hmm.
And so they can become one, if it's in an area, it could be left as pus, or they'll travel to places like the spleen, for example, and they go to die.
And they, what, get filtered out in a week?
Yeah.
Okay.
Yeah, it's amazing. They just, a lot of these leukocytes, and we're going to talk about macrophages, the eaters that do the cleanup, they're going to die.
Took a while.
Yeah. They do a good thing for us, and then they go bye.
Does that affect their body in any way?
It depends on if you don't have a spleen, for example, because you've got a car accident, there's other mechanisms that will take over that job of filtering anything that's dead in your body, kind of breaking it down and getting rid of it. Or if you're immune deficient for some reason, it's just more taxing. So, people who are immune deficient, oftentimes they have to rest a lot more because little things exhaust them for reasons of this. Just like little things that happen in your life are exhausting. Your body can get exhaustion from being sick. That's why if you got the flu, or when you had, let's say, if you ever had COVID, you know that it might take a month from that first day of feeling sick. You already had a few days before your first day of feeling sick of things happening. This whole army, this defense system of starting to work, that it's putting a lot of energy toward defending you and then cleaning up the mess and then recovering to get yourself back up to speed. So it might take like a whole month for you to go from that first day of feeling badly to feeling normal again. And sometimes it could take months for you to feel like, oh, I got my energy back. Because you have this whole defense system, you have a war that has happened inside of your body. So phagocytes are another branch of, or are a part, I should say, a kind of leukocyte that do the gobbling. They are going to do the consuming. They gobble stuff up. And then the phagocytes are more specific to microbes, things that are foreign in your body, not your cells. Natural killer cells, natural, thinking like it's part of your own body, that they are going to gobble up cancerous cells. We'll talk about them in a little bit. And then any cells of your own but are infected with a virus. So they're kind of doing taking care of your own cells that are infected either by cancer or a virus, and the phagocytes are doing the other stuff that's come into your body.
Is that why you get so tired after chemo, because your body's trying to make new cells?
Oh yeah, a chemo, if you have a cancerous cell, chemo is poison, and it poisons anything that's fast growing. And so one, you're dealing with the exhaustion of being poisoned, and then you're dealing with the exhaustion of that breakdown of those cells and cleaning them up, yeah. It's like a super war when you have chemotherapy.
Natural killer cells the same as killer T cells?
Yeah. So they're it's a different system, but very similar, yeah. There's one for, we have a whole system for bacteria and our own damage to our body, like I said, for spraining your ankle, for example. And then we have a whole other system for viral infected cells. So we kind of have two, depending on the kind of infection you get, or the kind of invader you have, you either have the B cell system or the T cell system. And we kind of do a little glossing over all of that specificity of the two different systems, just because this is kind of an introduction to the immune system. But if you ever take an immunology class, oh, it just, the immune system is amazing. Yeah, so there are two, so yes, similar is the short answer to my long answer. We also have an inflammatory response. So usually if you sprain your ankle, what does it do? It swells up. And the swelling up, that biggest part of it is to bring a lot of water to that area. So it gives more space for your immune system to do its job. Because if you didn't have swelling, it's all compacted in our normal, area, especially if you're thinking about the ankle. It's usually it's one of the slimmest parts of your body. If you sprain it, there's not a lot of room for the immune system to come and do their job of cleanup. So the swelling gives space for all of those parts of your immune system to move and work. So that's kind of inflammation. When you're damaged is a really good thing. A lot of environmental things in our world, we're hearing a lot more and more. A whole huge, somewhat new field of research that's exploding is a lot of environmental factors in our world cause us to have inflammation when we're not sick or damaged. And so inflammation, they're finding, is a very dangerous thing that happens just based on what you eat and how you interact in the world. And that we're hearing more about anti-inflammatory diets and foods and nutrients that are really important for us.
So the inflammation isn't really a result of the injury itself, it's the body's reaction to the injury, the body's doing it on purpose?
Yes, correct. Yeah, it's the inflammatory response when you're damaged or sick is a good thing. when you're not sick or damaged, it's not a good thing. And that's what we're looking, that's what that field of like the inflammation, when we're hearing more and more about inflammation in bodies and how inflammation is bad. That's where, when you don't have an immune response, a reason for an immune response, and you're having an immune response to things that you're putting into your body, that's not good. So again, hopefully this class, one of the things that I like for you smart students is to maybe consider, maybe you thought, I'm gonna be a pharmacist, and you have an idea of what that meant. It's so much bigger than what you might have thought of. And there's so much cool things, so many cool things happening in the world with research that you might go, oh, that I'm really interested in. And then, So one of the things that happens with the immune response, inflammation response, is that you have mast cells that will secrete histamine. Think about antihistamines that you might take when you have an allergic reaction, like an allergy to something like pollen or mold. We naturally produce histamine in our body. What happens is that when histamine is released into that area, it's going to stimulate the cells to increase blood flow to that area, or sorry, I should say it's released into your body, and it's going to increase the water flow to that area. So it's going to bring that inflammatory response there. Gives more space to work in. Also, the histamine, it starts to tell the phagocytic cells, the big eater cells, to come and clean up, do a cleanup. So we have a lot of things because the mast cells secrete the histamine. Yeah.
So when you take antihistamines to like reduce your swelling or your allergic reaction, is that technically kind of anti-productive?
Okay, so in this case, if it's a sprained ankle, yes. If it's pollen, okay, so coming up to this time of year, if any of you have a pollen allergy, that's seasonal allergy, or you have a mold allergy, that this time of year you might all of a sudden you're just like, oh, you wake up one day and you're feeling kind of rotten just a little bit, and you're like, oh no, I'm getting sick. And then the next few days, maybe you have a little bit of a fever and you're congested. It's probably just your allergy to pollen, not the flu. And maybe within 2 days, it's kind of like the fever has gone down and you're breathing easier. Some people take everyday pills because this happens pretty often, especially now with the climate changing so much that, like this time of year, you check the weather a lot because you don't know what the temperature is going to be like, right? We could have a 70-degree day. I mean, all winter it happens, right? We could have a 70-degree day, and sometimes if we have a couple days that are 70 degrees in January, the plants are like, oh, it's springtime. I'm going to start to produce more pollen or more, gametes, that they start to release them, and then it goes back to 10 degrees the next day. So we have a lot of confusion that allergies, seasonal allergies, could be all year long, just because we have such drastic changes in our temperature all the time. So an antihistamine, what that's going to do in the case of somebody who might take it for seasonal allergies, is that your response to pollen, which is just essentially plant sperm. Remember when you looked at pollen in your lab, when we looked at all of the different kinds of plants, that pollen is really, really small, but is that dangerous to you in general? Is a little piece of pollen dangerous to you? No, right? So what happens is that some of us just have weird genetics that in reaction to pollen, microscopic little plant sperm, that your body overreacts to it. Not everybody has that reaction, but some of us do. I know I have a mold allergy, so anytime it's like warm, the mold kicks up and I start to get congested. But it's not a mold that's dangerous to my body, but my body overreacts by going through this inflammatory response in my lungs. And so some of us just have that inappropriate reaction to something that's not anything that's really gonna cause us damage. So you take an antihistamine to try and prevent your body from doing that overreaction. So in some cases, yes, but you don't want it to be all the time, because what if it's a flu and you want that inflammatory response in your lungs to battle those viruses?
Yeah. Is that like the same like when you have like a allergic reaction, the nasal congestion, you can actually see, like, I don't know if you actually like looked inside, like when someone is, it looks like they're, I don't know if that's swollen or their nose is closed, is that histamine just swelling everything up?
Yep. Yeah, absolutely. So it's just trying to help to make a cleanup area. Yeah. So here's an example. Let's say that you get a cut. You're doing some yard work and one of the plants that you're working with has spikes on it. That spike might have some bacteria on there, which is bacteria everywhere, and most bacteria are fine, but your body's non-specific internal response is like, I don't know if this is a fine bacteria or a really bad one. It could be tetani, Clostridium tetani, right? It could be a bacteria that would cause you to have this area of your body to just totally like stop working completely. And so your body's response is that these mast cells detect that some tissue has broken open, and in response the mast cells are going to release histamine, and that histamine, you can see it's going to do a whole bunch of, it's going to start to contact all kinds of things in that area. And one thing is that they're going to do is that histamine is going to tell the circulatory system, hey, let's flow a little bit more over to this area. Let's bring those white blood cells, the phagocytes that are going to start to eat up these invaders here. And let's also cause some swelling in this area to make more room for them to squeeze into this area and have a little bit more space to work. Another part of your non-specific internal defense, your innate immune response, is a fever. And fevers come when things are, so I always like to think about it like this. So your body's, your immune system just kind of floating around, and it's at a homeostatic level. It's pretty equal throughout your body, all of those different kinds of white blood cells. If you have something that enters internally, and if it's something that starts to overtake the working of your kind of like normal white blood cell working or your immune system working, it starts to get faster in the beginning. What is going to happen is that you need a boosting of your immune system to start working faster and more efficiently. And so your body responds, it has this whole metabolic chain of reactions that goes to your brain, and it says, let's up the temperature a little bit. You're normally around 98 degrees, 99 degrees, but let's jack up that temperature. And what that temperature jack up is going to do is it's going to make your immune system start to work a little bit faster, so that when it's kind of here at homeostasis and the invader starts overtaking the ability of your regular immune response, it's going to say, go faster, faster, faster. And what we know about heat in general, just kind of basic principles of heat, is heat makes molecules move faster, right? Boiling water, you see there's some action happening, and that's what happens to your immune response, as your immune response ups. And this thing, one of the things about foreign invaders is in general, is that when the temperature in our body is jacked up, while we respond with a little more action, they start to slow down. So we have kind of two things that are happening there, is that this starts to go up and this starts to go down a little bit. And the hope is that then your immune system can overtake this invader. Fever in general is a good thing. So sometimes fevers get out of control though. And what is released by the macrophages to cause this whole chain of reactions throughout your body, this metabolic chain, a feedback response, is to release endogenous pyrogens. The hypothalamus is really small in your brain, but it does a lot. It controls a lot of what happens. It has signals to the pituitary gland, and it tells the pituitary, okay, I want you to do this. And then the pituitary, which is also pretty small, it does this. And then the pituitary tells the next thing to do something. So a lot of that originates in the hypothalamus in your brain. Hypothalamus begins that increase in body temperature, which causes the white blood cells to move faster and causes the infectious agent to kind of slow down. So if you have what's called a low-grade fever, about 101, 99, 100, 101, that you want to keep. So if you have have a low-grade fever and you feel warm and you take your temperature and it's kind of in that like up to 101 range, do not take a fever reducer. You want that low-grade fever because you want this system to work efficiently.
What medicines are the fever reducers? Is like a Tylenol like that?
Tylenol, aspirin.
Oh yeah?
Yeah, Motrin. Yeah, those things that don't take that.
So what should you take?
Nothing.
Just tough it out?
Tough it out. Because usually you kind of feel rotten, right? Like you feel a little like, because you do have a war going on, but you want that war. You want to push that. You want to encourage that war. But sometimes, and here's where it gets to be like, oh, here's where you need the fever reducer, is that so you know, like here's your immune system. It's working, and then somebody comes in and they start to overtake the immune system. And then the immune system, you get that low-grade fever and it pushes this up and it starts to push that down. If you take a fever reducer, it could encourage this level to come back up again. You could actually do like the opposite effect of what you want to do. So, but sometimes what happens is that your immune system comes up with that low-grade fever, but this thing it's taking ground, it's doing well in your body, and it starts to overtake your immune system. And that's where you start to get those higher fevers, and that's where you want the fever reducer, because you want you want like this to come down. So you don't want, it has nothing to do with this system. It has more to do with you don't want to cook yourself. It means that you probably need more medical assistance than what you can naturally do. And so if you've ever had where, like the system is working and then, and the fever, your body's response is, let's keep trying to get this to happen, and it's not doing it, this isn't working appropriately, and you get one of those higher grade fevers, you probably need to go to the hospital, or call a medical professional and be like, can you do something for me? Go to urgent care. I genetically have typically overreactions to invaders, and so my son has it as well, is that when we are sick, even if it's just allergies, we end up having like 104 fevers from like anything. Is that I have to monitor both of us, really closely because we can kind of get way too hot quickly. When my son was 1.5, he had something, and he had a 106.9 fever. I was watching it, and it just went it went from like 102, shot up to 106.9, like within an hour. And so we go to the hospital, and they're like, oh, it's fine. Babies can have like really, really high fevers. It's not that big of a deal. And I was like, I don't care. Because what if it just kept going, right? And so they gave him a bag of stuff and IV, and it came down. But I was like, And she was like, you know, in the future, and I was like, in the future, I'll meet her again. Because I just don't know when it's gonna stop, when the ceiling doesn't ever get hit, and you literally start to cook your body with that heat. So, genetically, you gotta, like, that's one of the things that I know with my son that I gotta be really careful about. And so anytime I fill out a sports form, I say if he has a fever, you need to monitor him super closely. Like the school knows, everybody knows, his coaches know. And like anything happens, he's gotta go to the hospital if he gets over like 103. He's gotta go. So, depends on you. All right, so now, all of that non-specific stuff, if it's not working, you sprain your ankle or you get a cut, and like I said, usually, the next thing that's gonna kick in is you're gonna have a very specific response to what is happening. And so what we call that is we call that the adaptive immune response. Your body is going to fully adapt to what is attacking you. It's gonna get specific. Sometimes we call it the specific immune response. I like to think of these as like defense systems. Like you've got kind of like the not so great, you know, kind of just, they can just do their job, but they don't have to like think too much about it. And then you've got like the next one that they think a little harder. This one, they're like, they've taken the MCAT, the PCAT, the everything CAT, the every test, they're the top line in your body, the smartest of the immune system. And they're gonna really work hard and be specific to what is going on. And there's different groups that do different things and they work together. And so it's like a big, almost like the army. They're going, this is a war. This war is waged. They're gonna like make sure that they can beat this one. Okay, so they are going to do things where they mark cells that shouldn't be there. Could be like bacteria. I just read about this morning in the New York Times said there's a fungal infection in some healthcare facilities that's starting to go around. It is not cordyceps, by the way. It's something, I can't remember. Candida, it's a candida, which candida is one of the things that causes vaginal, what do you call that? A yeast infection, thank you. Yes.
Oh, that's what it is?
Yeah,
Oh.
yeah, so it's a kind of a yeast that's going around.
How, is it just like how?
Sorry, and then, so I don't freak you all out. It's more so targeting people who have very compromised immune systems.
How does it travel?
I didn't get that far because I did a bad thing. I was sitting in traffic and read the title and started to read the first paragraph, and then we started going, and then I was like, oh, that's dumb. Wanted to make sure I didn't have to activate this by getting in a car accident. So anything that you have like that, fungus, bacteria, or if you have a virus and virus targets our cells, virus particles are so fascinating in that they're not a full cell, right? They're not alive, but then they like get into our cells, and we talked about different mechanisms of that. They get into our cells and then they work with our own genetics to program our cells to make more of themselves. So really brilliant genetics for something that's not alive. So it could be a viral infected cell, it could be a cancerous cell. So all of these things will be specific, like we talked about before. There's different teams that do that, but they're going to target the cells by flagging anything that doesn't belong there. So a foreign cell, a foreign particle, or a cell that is infected with foreign particles like viruses or cancer cells. So we've got a lot of different what ifs, this happens, what if this happens. So one team are the B cells. The B cells differentiate, meaning they become specific. They go from being like generic cells, just a generic white blood cells, to a very specific kind of white blood cell in the bone marrow. B, bone marrow. We call this the humoral immunity. The B cells are typically anybody who's not part of our own self. So cells that come into our body, cells that come into our body, bacteria, fungus, protists, anybody who's not a self cell.
Sorry, you said that they target non-self cells?
Yes. The T cells, and I have that somewhere in these notes too. The T cells, they differentiate in the thymus, T for thymus. This is what we call the cell-mediated immunity, because these ones are dealing with something's gone wrong with our own cells. Cancerous cell or a cell that's infected by viruses. It's starting to produce virus cells. So this is other stuff, this is our stuff.
Like apoptosis.
Yeah, they'll do that. Okay, so job one, they just need to recognize. Your immune system is like, something's happening that shouldn't be. Somebody's here and it's affecting us in a way that it shouldn't. So the first job is recognition. The way that recognition happens is through surface markers. I love this picture. So this is what your cells look like under an electron microscope. Notice the surface. So, like in your textbook, maybe Bio 111, you looked at a cell, and it's like the nucleus, and like phase, and there's phase, and... Okay, so it just shows it like that, right? Really generic. The plasma membrane is flat. It's not flat. When you take this section and you look at it more closely, it looks like a tennis ball. And what those little fuzzies that are sticking out, those are surface markers. And those surface markers have all kinds of information about that cell, about you as an individual, and about you as a species. And so the surface markers, any surface marker on any cell, which includes, we're talking about bacterial cells, or you're talking about like a fungus cell. We all have these surface markers. I should make that one a different shape. That these surface markers have information about you, about this fungus, about this bacterium, that it tells things like, I'm this kind of species. So we have species markers, and one of the things, if you remember a little bit when we talked about plants and genetics, that the surface markers, like let's say our surface marker is square shaped, and this bacterial surface marker, not the bacterial but a lot smaller, scale is back here, this would be enormous in comparison to these, but the surface markers, they don't fit together. This doesn't fit. So your white blood cells that are floating around are basically going like, boo, boo. They're going up to cells in your body constantly and kind of doing like a little handshake, fist bump, whatever you want to call it, is that they're going, yep, you fit, your surface marker for species fits, you fit. Wait a minute, you don't fit. Put a little flag, they're gonna bind, well, first thing they're gonna do is they're gonna bind to it. They're gonna be like, I'm gonna do a thing where I'm gonna actually like tag onto you, and then this whole chain of events happens. Is that cell, the first cell that recognizes that the surface markers don't fit, is going to do something where it merges with that foreign cell, and then they're going to start to replicate themselves, and then they go through a chain of events where they end up making antibodies or T cell receptors, depending on which team we're talking about, the B or the T team. And then it's going to produce a lot of, like if we're talking about B cells for bacteria, they're going to produce all kinds of antibodies. So little things that are going to tag onto here. And once these are flagged, any foreign cells are flagged, it tells another kind of cell, come and gobble this, because it's got a flag on it.
So an antibody is a flag?
The antibody is a flag.
Okay, I didn't know that.
Yes.
I just know that like antibodies are good for.
Yes, and these little flags stick, they're little Y-shaped flags, they stick around in your body. And the top part is like a circle. So it's a little thing that's going to be the shape of this surface marker, so that if another one comes along later in your life, it'll, oh, we fit together, the antibody fits with it, and it holds on to it, and then a white blood cell's like, wait a minute, that's flagged, let's eat that up.
Okay, cause like your whole life you told that like antibodies are good, but like I never knew what they were.
Yes, they stick around from past infections, and so that if that infector comes back again, the whole thing about the whole like antibody or what we call T cell receptors is that you have these little tiny flags that are floating around in your body, so that if they encounter something that you already had this full-on war with, because what happens is with a white blood cell is that the first time that they're like, boom, yes, yes, no, they have to merge with that cell. They have to start to replicate an army of themselves. That army will make more of those that can keep doing that like checking of this invader, but then they also make an army of cells that just replicate and pump out antibodies or tiny little flags. So instead of having to go through this whole system where they merge and then they start to replicate and replicate and replicate and make an army themselves, they pump out the little flags. All that has to happen is like the next time the invader comes, the flags are already there. You don't have to go through 10 steps to make the flags. And then it takes a while to do this catch-up thing, that the flags are there, and that they can just like, oh, wait, I'm gonna flag this, and a white blood cell can come and gobble it up before you have the full-on war.
So do they die after a while, and that's why you
They do.
why they go down with them?
Yeah, they do. The system, anybody who flags, any white blood cells who do the flagging eventually give up their lives. Or any of them that come across a cell that has a flag on it, gobble, 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 they give up their life too. That's why, like, part of the healing, you know, like you get sick, maybe for 2 weeks you feel awful, right? You're ramping up to feeling really, really awful, and then you're kind of ramping back down to feeling normal again. Like if this is your homeostasis, you're going like, war's happening. The recovery part takes weeks also, because everybody who's given up their lives has to be gobbled up themselves. They have to be filtered out, broken down and filtered out, and replaced. So the war and the recovery, which is worse, they're both taxing on your body to get you away from homeostasis, to have the war, and then get you back to homeostasis.
We had a question.
Oh,
Yes.
I thought I did this. Okay, thank you. A microbe is trying to infect you. Which of the following represents the correct order of defense for the microbe will encounter? Which one you said, D?
Yeah.
Yeah, good, yeah. So it'll encounter the barriers, the non-specific external, the non-specific internal, and then it will be the specific immune response. Good. Okay, so moving to a lot of stuff that I already covered in my little example. So antibodies go with the B cells. T cell receptors go with the T cell system. The T cell receptors are very similar to the antibodies. And sometimes and sometimes these go hand in hand too. I don't wanna get too much into it, the complexity of like COVID, for example, because it's very, very, very complex. So we're gonna just think about for today, 2 systems, and the B's contact anything that's not our cells, and the T's, anything that our cells have infected or cancer cells. So our own cells are infected, or other things are happening inside, other invaders inside our body. Okay, so let's look at an antibody, and this works again, it's very antibody for the B cells, and then very similar to what happens with the T cells. But we'll use one as an example. So, one of the things that happens is that your immune system, when we're talking about an antigen, antigens are surface markers. The binding, what's going to come and bind with them is going to be the antibody. So think about I know we call it an antigen, but think about it as an antigen, an antibody. Antibody, not your body, right? But we don't say antibody, we call it an antibody. So just think about the word. Antibody means not your body, not yourself. So you're in response to a foreign antigen, a surface marker that's on a bacteria, a fungus, a protist. That what's going to happen is that your body is going to produce an antibody in response to this antigen, the antigen.
So the bacteria that they're attacking, that bacteria has antigens on it?
Yeah, it has surface markers that are specific to this,
To the bacteria?
to the bacteria alone. The fungus has antigens specific only to the fungus. We have antigens specific only to us. So like if our cells infected something else, I mean, it could hypothetically go in a different direction where we, like COVID, if you got COVID and you infected your dog. So on some cases, it kind of goes like, COVID's not the best example, but it could go the other way. We could be the infector, but we think about us. Who's infecting us? So these are the surface markers that say, I'm this species of bacteria. It also has all kinds of other information. And this class, again, we could go on for hours and hours. The immune system, you could take a whole immunology class, and it lasts a semester, and you still don't cover everything about the immune system. You could take a PhD. You could do a whole 5 years about the immune system and still not cover everything. That's how complex these topics get. So just kind of in general, when we're talking about these surface markers, the surface markers, like we're talking about like our own surface markers on our cells, they'll say things like, I'm a Homo sapien, I'm Michelle Zarowski, I'm a red blood cell, I'm a red blood cell, I'm an Rh negative red blood cell. So they've all got like little pieces of information that stick out about that cell. It's not just one piece of information, it's many. Okay, so the structure of the antibody, it's like a letter. Oh, wait, I'm so confused.
Clock when all the clock is on.
What time is it?
It's 9:09.
9:09, okay, so I've got a few
Yeah.
more minutes.
I walked in and it was at like the 2, and I was like, it's not 10. I was like, I'm the first person in here.
Yeah, I don't know. The antibodies are in the shape of the letter Y. The base of the letter Y, it's the same for every antibody in your body. They're called constant because they all have the same base. It's just like if you go to Home Depot and when you go to get a key made, or like there's those machines now, right? There's like the machine has a whole bunch of blanks in it, right? And then you choose which blank you want. And then, so that's like the constant region, is that it's a blank letter Y. It's just like generic. What's gonna be put on is gonna be specific in shape to every kind of antigen, and that's what takes a little bit of time. The good thing about having all these blanks floating around in your body is that we can start with a base that we don't have to go and make. So it speeds up the time a little bit, even though it does take a while for the antibody system to be made, or the antigen. But the good thing is at least you have the base. Because otherwise it'd be like, if you go to Home Depot and you're like, I have this key I want copied, and the person takes the key and they're like, oh, okay, you know what, I gotta go in the back, and I gotta take the hot metal, I gotta pour it into a mold, and I gotta make the base, right? That would take even longer if they had to go and make just like the blank keys, right? They're already there for you. So that's like the constant region. Is there generic? There's nothing specific about them except for like, it's a Homo sapien antibody. The variable region is the tips that are gonna bind to the antigen shape, the antigen surface marker, the invader's information. Every invader has a different top shape. So even if you're talking about like the difference between like Clostridium botulinum and Clostridium tetani, even though they are the same genus, they are going to have a different shape, surface marker. So here you can see the antigen surface marker, it's going to bind the top part with that. This is going to be the same for everything in your body. So like for example, if you've had 3 different infections from 3 different invaders, this is the same for all 3 antibodies, but this is specific to this invasion, this is specific to this invasion, and this is specific to that invasion. All right, how do we tell the difference between your self cells and your non-self cells? Yeah. Oh, question? Thank you. Triclosan is a common antibiotic used in antiperspirants, toothpastes, antibiotic soaps, and lotions. If you don't believe me, check your labels. Which of the following is most likely the prediction about this antibiotic? Like you can read sideways. All right, what do you think? I know there's a lot to read, sorry. Agree? C? Everybody? Okay, yeah, good C. Okay, why don't we stop there? Kind of on time, maybe a minute early. And then we'll talk about how do we identify ourself versus non-self, and we'll get into